Hello chemists, this is Miss Placino and you're watching lesson 12.5 on reactions of acids and bases. In today's lesson we're going to talk about two different types of acid-base reactions. Goals for today's lesson include being able to label conjugate acid-base pairs in reactions. This is really a Bronsted-Lowry definition, application of acids and bases. And the big one is being able to predict the product of Arrhenius acid-base neutralization reactions. So lots of equations to look at today, hopefully reviewing some topics that we covered during the first semester. All right, let's get started. We'll start with Bronsted acid-base reactions. Hopefully you remember that a Bronsted or Bronsted-Lowry, really both names are kind of talking about the same concept. Bronsted acids are going to be proton donors and Bronsted bases are going to be proton acceptors. So really, when these two substances react with one another, we're just going to see a proton being passed from one material to the other. The example that we've looked at a couple times now is ammonia reacting with water. We know in this case ammonia is going to be our base, our proton acceptor, and water is behaving as an acid. Remember, we're not saying that water is acidic. If you were to try to take the pH of water, it's still going to be 7. But in this case, because it's behaving as a proton donor, it is behaving as a Bronsted-Lowry acid. Effectively, what happens is one of the hydrogens from water is going to be donated to, in this case, ammonia. You think about it as like the lone pairs taking it, the hydrogen being donated, just a transfer of hydrogen from water to NH3. That will end up producing NH4+, this ion, and the hydroxide ion. And this is why ammonia is a basic substance. It is able to create hydroxide ions in solution. It just does it kind of in a roundabout manner. Since we're talking Bronsted-Lowry acids and bases, notice that the reaction arrow is reversible. You can imagine the reverse reaction occurring. One of the hydrogens on the ammonia gets passed back to the now hydroxide ion, and we reform the initial reactants. So in that case, we have NH4+ behaving as an acid, and since it's on the product side, we'll call it a conjugate acid. And we have hydroxide behaving as the conjugate base. It is accepting the proton from the ammonium ion to reform water and ammonia. So again, our acids and bases are going to be on the reactant side, so to the left of the reaction arrow. Our conjugate acid and conjugate base will be on the product side, and that's just kind of a naming convention. We can pair up the acid and its conjugate base and the base and its conjugate acid. So again, we know we've already gone through and we've labeled which substance is behaving as acids and bases on both sides of the equation. And a base gets paired up with its conjugate acid. So we would pair ammonia and ammonium, as they're different by just one proton. And that will leave us to pair up our acid and our conjugate base. So water on the reactant side and the hydroxide ion on the product side. So that's what we mean by conjugate acid-base pair. Let's do some practice problems just trying to reinforce this concept. All right, so we've got question 1 being asked to label each substance as either the acid, the base, conjugate acid, or conjugate bases, and then draw a line connecting our conjugate acid-base pairs. So we'll look at that top row of problems. We've got HF and NH3 as reactants, then I create NH4+ and F- as products. So it seems like hydrogen fluoride becomes F-, so it lost a proton. So a proton donor, that is an acid. That means ammonia is behaving as a base. Let's double check and make sure it's being a proton acceptor. So let's see, NH3 becomes NH4+. Yes, that is a proton acceptor. And the reverse reaction, ammonium, NH4+, is donating a proton back to the fluoride ion. So it's behaving as a conjugate acid, making fluoride the conjugate base. I always pair up my acid and conjugate base, and my base, and my conjugate acid. Pause the video, try out these next two in the same row, and then we will have the answers posted so you can check your work. So in the middle problem, I've labeled HCN as my acid because it is losing a proton. It's donating a proton as it goes from reactants to products. That makes water as my base in this example because it's accepting a proton. In the reverse reaction, H3O plus is donating, so it's a conjugate acid. The cyanide ion is accepting a proton, so it's behaving as a base. So I have my conjugate acid-base pairs. There we go. Last one, I think this one's a little bit more complicated since you've got, potentially two substances that can behave as acids and bases. We've got HSO4 minus donating, so it's behaving as an acid. HCO3 minus accepting, so it's behaving as a base. And the opposite is true on the product side of the equation. We've got sulfate accepting a proton, so it's behaving as a conjugate base. And that's carbonic acid, H2CO3, is donating a proton, so it's behaving as our conjugate acid. We always pair them up, acid with conjugate base, base with conjugate acid. And that's all there is to it. So hopefully that makes sense. You've got those 3 other practice problems to play around with just to reinforce that concept. Let's get back to the notes. The type of neutralization reaction that I really want to focus on involves Arrhenius acids and bases. These neutralization reactions really take on the same format every single time. We have an acid reacting with a base. Both of our reactants will be aqueous. We form a salt, and when we say salt here, we just mean some form of an ionic compound, not necessarily table salt, NaCl, and water. It's the same general reaction again and again and again. We neutralize to form salt and water. The actual neutralization itself is more between the hydrogen ion and the hydroxide ion. They're going to come together to form water. They'll go from being aqueous ions to being a liquid, so they're the ones that are really taking place in the neutralization reaction itself. This is going to look like a double replacement reaction, something that we talked about during Unit 5. We've got 2 reactants and 2 products. Everything is a compound, double replacement. These should be a little bit easier than your typical double replacement reactions since one of the products always ends up being water. So really, the hard part is trying to figure out the identity of the salt, making sure that you've got its formula predicted correctly, and then just being able to go through and balance. As you probably would imagine, the identity or the formula of the salt is really going to depend upon which acid and base have been used to neutralize each other. So let's go ahead and look at a couple example problems together. All right, so I'm going to look at question 2A to get started. We've got H2SO4 and NaOH. This is definitely an acid-base neutralization, and I know that one of the products is going to be water. So I'm just going to kind of write that right off the bat. Why are you putting in the second blank, Ms. Placino? Well, that's where I felt like putting it. It doesn't matter if I put it in the first blank. No, it does not matter at all. Make sure you are producing water. A really common rookie mistake that I see is students doing, okay, I got H2, I have OH, so that means I must have H2 plus 1 is 3. Oh, no, that's not how that works. We're always going to be producing water. We'll deal with, there being like an extra hydrogen, as it might seem, when we go to balance. We know that sodium has a charge of +1. Sulfate, you can either use the formula H2SO4 or you can use the reference table to figure out its charge. Either way, you should end up with 2-. So when I go to predict the formula of our salt, sodium sulfate, I have crisscross method would give me Na2SO4. Get that out of the way. So in my opinion, that's really the hardest part, is trying to figure out what the formula of the salt will be. We'll go through and we'll balance. Now I see 2 sodiums. Now I've got 2 sodiums there. A sulfate, good. I have 2 oxygens, 2 hydrogens, plus another 2, so 4 hydrogens. Oh, so I put a coefficient of 2 in front of water. That's going to take care of the balancing. You'll notice that I've also asked you to name the acid, so kind of reviewing lesson 12.1, and then identify the strength of the acid and the base. So that's lesson 12.3 review. H2SO4 is sulfuric acid. Sulfuric acid is a strong acid. We've got sodium hydroxide. That's a group 1 metal combined with a hydroxide, so that's going to be a strong base. If you find yourself constantly flipping back to that page in your notes where you have the strong acids and strong bases listed, that is proof positive that you need to spend a little bit of time memorizing your 7 strong acids and your 8 strong bases. So definitely worth your while. We're going to be continuing to build on this as we go. Try out question B. Go ahead, pause the video, give it a shot, and we'll check your work when you are finished. All right, H2CO3 is carbonic acid. Whoops, wrong tool. I know when carbonic acid reacts with calcium hydroxide, a neutralization reaction occurs. That means I am going to produce water and some salt. I have calcium. I know that's a 2+ ion. Carbonate is a 2- ion. So I will produce calcium carbonate. Let's check and see if I'm balanced. Calcium and carbonate look okay. Water does not. I'm going to need a coefficient of 2 in front of H2O to balance out my hydrogens and oxygens. Carbonic acid is a weak acid. It's actually present in things like soda and seltzer water, and you definitely would not want to consume a strong acid. Base strength, calcium hydroxide, that is one of our 8 strong bases. So let's put an S for strong. As always, I would really encourage you to go through and work with the practice problems. Make sure that you can predict your products of these neutralization reactions and review things like naming and acid and base strength. Again, it'll prove to be really useful for some of the other applications and lessons that we go through this unit. All right, that wraps it up for today, chemists. Thanks for tuning in, and I hope you found this helpful.